Alright, in today's video we'll look at the melting and boiling points that are found at the back of your Grade 9 Advanced Science booklet on the back of the solubility chart. I've got here a little picture from the solubility chart. It lists the freezing points or melting points of various substances and their boiling points in degrees Celsius. So one simple thing we might be asked to do with this is to sketch a heating curve or to sketch a cooling curve. For example, let's take a look at on that list of substances. Why don't we take one that we're a little bit familiar with? Let's take lauric acid. We did a little lab activity with lauric acid to determine its melting point. Let's sketch the cooling curve of lauric acid. So the cooling curve of lauric acid, you know that a cooling curve is a graph. It'll have a y-axis, a vertical axis where you list the temperature in degrees Celsius, and it'll have an x-axis, time. And the units for the time here don't matter because we're just sketching a curve. When you look at the data on lauric acid, we notice that it has a melting point of 44 degrees, 44.1. It has a boiling point of almost 300 degrees, 299. So on this sketch of a cooling curve, let's start up here at 350 degrees Celsius. And let's go down, let's see, 350, let's go down to 250, then to 150, and then over here to 50. All right, so this would be 0 degrees Celsius on that scale. All right, so that's our temperature scale. Now let's suppose we start with a sample of lauric acid at a really high temperature. We're going to start up at 350 degrees. So I'll use a different color for this. 350 degrees is our starting temperature. Well, at that temperature, would you expect the lauric acid to be a solid, a liquid, a gas? That temperature is above the boiling point. If it's above the boiling point, then the liquid has already boiled completely, and now you have only gas, you have vapor. So we have really, really hot vapor of lauric acid, and then we slowly let it cool down. Now we know at 299 degrees, almost 300 degrees, it's going to turn from a gas back to a liquid because that was the boiling point. So if you're cooling it down from a vapor, it'll be a condensation point, the opposite of boiling. So we're going to see the temperature drop, and then it's going to hit 299, which on my scale is right very close to 300, and we're going to see a plateau there. The temperature will suddenly stop changing. That plateau is where it's turning from a gas back to a liquid. At the end of that plateau, there's no more gas, it's now completely liquid. Then the temperature will start dropping again. And as it drops, it's going to continue to cool. We look at the data at 44 degrees is where it will freeze, right? The opposite of melting is freezing. So the liquid, as it cools, will eventually freeze. On my scale, 44 degrees is down here below the 50, about there, roughly. Now sometimes you see super cooling, so I'll suggest a little bit of super cooling. And then, whoops, I'm getting a bit of sloppiness with my sketch. There's another plateau, and then it'll continue to drop when it's finished freezing. So on this sketch, the temperature was dropping initially, and then it began to plateau. I'll draw a dotted line there. It finished plateauing over here. I'll draw another dotted line. The supercooling is that little dip before the second plateau. Right in the middle of the supercooling, I'll draw another dotted line. And at the end of the second plateau, I'll draw another dotted line. Now, what do those dotted lines represent? Well, in the first region, we had just gas, right? So at that part of the curve, there was only gas present. In the second part of the curve where you saw that plateau, that's where we had condensation happening. The vapor or the gas was turning back to a liquid. So in that section of the curve, during that time interval, you have both liquid and gas. The vapor, the gas, is turning to a liquid, condensation. And that's happening at the same temperature as the boiling point, 299 degrees Celsius. At the end of that plateau, the gas is now completely condensed to a liquid. So in this middle section here, we have just a liquid, and the temperature is dropping. At 44 degrees Celsius, it should have cooled, it should have frozen, but the temperature dropped a little bit below that, and it still remained a liquid. That is where we have supercooling occurring. And technically, the freezing doesn't start until you see the temperature start to rise during the supercooling, and then it begins plateauing. So that's why we put the dotted line in the middle of the supercooling. That's where freezing began. So freezing is along that middle, that second plateau. During the freezing, you'd have both liquid, you'd have mostly liquid at the beginning, and then you start to see more and more solid and less liquid. At the end of the plateau, liquid is now completely gone, and now you have just solid. So those are the parts of the cooling curve for lauric acid that we were able to sketch just by looking at the melting and boiling points on the data chart there. If you were asked to do a heating curve instead of a cooling curve, you would have still had the same y-axis, the same 0 to 350 degrees, but your graph would have been heating up. So it would have started at a very low temperature, it would have been a solid, it would have risen to 44 degrees where there was a plateau. That would be the point where the solid is melting. After melting, the liquid would have risen temperature up to 299, where there'd be another plateau. That would be the boiling plateau. And when it finished boiling, the temperature would rise again when it was just vapor. The graph would look like this, the mirror image of it. So that's one use of this data to sketch cooling curves or sketch heating curves. Another common question that you're asked is to predict for a given substance whether it would be a solid, liquid, or gas at a given temperature. So is it a solid, a liquid, or a gas at some temperature degrees Celsius? So let's do a couple of examples. Suppose you have mercury, that's one of the substances on the chart, and let's give it a temperature. Mercury at, let's say, minus 30 degrees Celsius. Okay, what would be the phase, solid, liquid, or gas, for mercury at minus 30 degrees Celsius? Well, first find mercury on the chart there. Let me erase my lauric acid highlighting. So the mercury is here, and we notice that its melting point, or its freezing point, is minus 38 degrees Celsius. So what does that mean? If that's the melting point or freezing point, when the temperature is below that, then you'd have a solid, right? And when the temperature is above this, you'll have a liquid. But then there's also a boiling point of 356. So how long will you have a liquid? You'd have a liquid at any temperature between minus 38 and 356. At 356 degrees, the liquid will start boiling. So at any temperature above 356, you'd have a gas. So thinking about that sort of as a number line, if you look at those temperatures and imagine that they were on a number line. Okay, so here's my number line. So minus 38 degrees Celsius is the freezing point. So if the temperature is below minus 38, you have a solid. When the temperature is above 356, so to the right of the 356 degrees, you'd have a gas. And if the temperature were above the melting point, but not yet at the boiling point, if it were in between, then you'd have a liquid. So for mercury, when would it be a liquid? It would be a liquid at any temperature between -38 and 356. When would it be a solid? At any temperature below -38. And when would it be a gas? At any temperature above 356. So we're asking for what phase would it be at -30? Well, on our number line, -30 would be somewhere in here between -38 and 356. So mercury would be a liquid at that temperature. So the answer here is liquid. Okay, try another one, this one on your own. Suppose you have 2-propanol. That's an alcohol. And let's give it a temperature of, let's say, 60 degrees Celsius. What would be the phase? Would it be a solid, liquid, or gas at 60 degrees Celsius? Pause the video and see if you can figure that out. So 2-propanol is down here. It's also known as rubbing alcohol or isopropyl alcohol. Its freezing point is -89, so at any temperature below -89, it's a solid. And then at any temperature above -89, all the way up to 83 degrees Celsius, that's where it would be a liquid. And at any temperature above 83, it would be a gas because it's boiled. 83 is the boiling point. So 60 degrees is in that middle section between -89 and +83. So like the mercury at -30, this guy would also be a liquid, but this time at 60 degrees Celsius. All right, how about naphthalene? Naphthalene, mothballs, naphthalene. And this time let's give it a temperature of, say, 30 degrees Celsius. What phase would naphthalene be at 30 degrees Celsius? Pause the video and see if you can answer that. So naphthalene is here. It melts. The melting point is at 80.6 degrees. So at any temperature below 80.6, it would be a solid. It melts at 80.6, so above that temperature, it's a liquid. It boils at 218, so above 218, it's going to be a gas. So we're asking at 30 degrees Celsius, so for naphthalene at 30, that would be somewhere over here below the 80.6 degree melting point, so it would be a solid state. All right, so that's a simple use of this data to predict whether the substance is a solid, a liquid, or a gas at a given temperature. Now, one last question you might be asked with this data table. Suppose we gave you a certain temperature, let's say 25 degrees Celsius. And let's ask the question, which of these substances are liquids at 25 degrees Celsius? So of all of the substances on the chart, which ones are liquids at 25 degrees Celsius? Well, remember that for any substance, it is a liquid when the temperature is higher than the melting point, but lower than the boiling point. So that's where it's a liquid. Higher than the melting point temperature, but lower than the boiling point temperature. So if I want a substance which is liquid at 25 degrees, it has to have a melting point above 25 degrees. So let's go down the list. Aluminum, well, its melting point is 660, so 25 is below that. Aluminum would be a solid, not a liquid, at 25 degrees. Ammonia, -78 is the melting point. So 25 degrees is certainly above that, so maybe ammonia is a liquid. We look over, though, and notice that its boiling point is -33. 25 degrees is above that. So that means 25 degrees, it will have already boiled. Ammonia would not be a liquid, it would actually be a gas at 25 degrees. The bromine, 25 degrees, is above its melting point, so maybe it's a liquid, and 25 degrees is below the boiling point. So yes, 25 degrees is in that middle section, so that means the bromine would definitely be a liquid at room temperature. Pause the video and see if you can find others that would be liquids at room temperature. Alright, so going down the list, the next thing that would be a liquid at 25 degrees Celsius, looks like ethanol would be a liquid because minus 14 is the melting point and 78 is the boiling point. 25 degrees is in between those, so ethanol is a liquid at 25 degrees. Another one that would be a liquid would be mercury. Mercury melts at minus 38 and boils at 356, so 25 degrees is in between those. Mercury is a liquid at room temperature. Methanol, also for the same reasoning. 2-propanol for the same reasoning, and water for the same reasoning. So those are all liquids at 25 degrees. One last one, suppose you want to find substances that are gases at 0 degrees Celsius. Which substances are gases at 0 degrees Celsius? Pause the video and see if you can figure that out. So to be a gas, the temperature has to be above the boiling point. So we're just going to look at the boiling point temperatures. So if I want something to be a gas at 0 degrees Celsius, 0 degrees must be higher than the boiling point. 0 degrees for aluminum is not higher than its boiling point, so not surprisingly, aluminum is not a gas at 0 degrees. Ammonia, the boiling point is minus 33, so 0 degrees is above that, so ammonia would be a gas at 0 degrees Celsius. Now there's one that's a bit tricky, and that's carbon dioxide. Carbon dioxide at minus 78, it doesn't actually melt, but it sublimes, and the sublimation is to turn from a solid directly to a gas. Since 0 degrees is above minus 78, carbon dioxide is a gas at room temperature. So that one's a bit tricky because it involves sublimation. The next one would be chlorine. Chlorine boils at minus 34. 0 degrees is above the boiling point, so it would definitely be a gas. Hydrogen boils at minus 252 degrees Celsius, so at any temperature above minus 252, including 0 degrees, hydrogen is gas. And then we have oxygen, not surprisingly, is a gas at 0 degrees. And I think that's it on this list, things that are gases at 0 degrees. Things that say decompose, just a quick note about that. Take citric acid, for example, or potassium nitrate, or sodium nitrate. If you started with a solid for any of those three substances and heated it up to their melting points, they would turn to liquid. But as you keep heating up the liquid, instead of boiling at some high temperature, the chemical starts to decompose before it boils. So they don't have boiling points. They simply decompose in a chemical reaction into other things. So they melt, but they don't boil. That's why there's no numbers, and they just say decomposes. So I hope that helps. Hope you understand freezing and boiling points and can use them to sketch heating curves or sketch cooling curves, to predict phases at different temperatures, or to identify which substances are a given phase at a given temperature.